To start this video, we're going to do a little review. So I want to ask you a question. Which of these is the most stable conformer of ethane and why? Now the why is the important part. So go ahead and pause the video, answer the question, and then we'll go on. So if you're looking at these two conformers, you probably did correctly assess that this, which is the staggered conformer, is the most stable. And the why is the reason where you may have gotten a little off track. You may have said, hey, well, these eclipse, they sort of run into each other, they collide, those electron clouds interfere. And if we stagger them, we get these as far apart from each other as they can, and that's what leads to the most stability. Now, I will say that's a great reason, and it's mostly correct. But there is one element we need to talk about that really ends up influencing a lot of organic chemistry and shows that there's a better reason for why that is the most stable conformation. And that is hyperconjugation. All right? So we need to talk a little bit about what is hyperconjugation and what does it do for us. All right? So hyperconjugation has to do with this. If we look at an ethane and we review what bonding orbitals are, we'll remember, if I draw this ethane out here, let's just draw a sort of a perspective formula here. The most stable conformation, right? So this is our staggered conformation right here. And let's go ahead and make things a little happier. There we go. So this is going to be our most stable conformation. And I want to talk about why. Well, if you review, what are these bonds here? What is this bond really? That bond comes from the overlap of an sp3, right? This carbon has an sp3 orbital, and this hydrogen has an s orbital. And when those overlap, we get something here that we call that sigma bond comes from the S and the sp3. But we can never take two orbitals and form one. Two orbitals must always form two orbitals. So what else do we have here? Well, we must also have an anti-bonding orbital. And that's going to kind of live out here like this. And this is going to be a sigma star, and that is an anti-bonding orbital. Now, are there any electrons, first of all, in the sigma orbital? Are there any electrons here? Yeah, of course there are, right? Are there any electrons in the anti-bonding orbital? No, it's empty. So the reason this bond forms and is strong is because this anti-bonding orbital, which is higher in energy than the sp3 and that s orbital, is empty. But the bonding, or the sigma orbital, which is lower than both of those, is full. So this is a favorable interaction to lower energy, and we end up forming a bond here. Now, if we look at this, what we'll notice is something very interesting here. We'll notice that if we look over at this other hydrogen right here, it also has a sigma bond right here, doesn't it? Yeah, that hydrogen has a sigma bond in the same exact way. And it also has these sigma star bonds. And you know what? I'm going to cheat a little here, and I'm going to empty these out just to show that they're empty, all right? Because there aren't any electrons in those anti-bonding orbitals. Now, if this is in the staggered position as I've drawn it here, what we'll notice is that these hydrogens are perfectly in line with each other, these anti-hydrogens. And because they are perfectly in line with each other, we'll notice that these electrons right here that make up that bond, when they're perfectly lined up like this, can actually sort of share some resonance or share some density with this sigma star antibonding orbital. let me review how that's possible. If you go back in time and remember what a pi orbital is, a pi orbital comes from when we have two, let's say, carbons here, and they have p orbitals, and those p orbitals are able to form an interaction, and we call that a pi molecular bonding orbital, because those electrons are able to resonate between those p orbitals and form that new waveform, that pi molecular orbital. Well, in the exact same way, these overlap with each other in something called hyperconjugation, and it's able to share that electron density. Now, this isn't a bond, it's not even close to a bond, right? Because if we put those electrons all the way in the anti-bonding orbital, it would actually break that other bond, right? Because we can't put those electrons all the way in there. But we can share them there, which stabilizes this bond over here and stabilizes us in our anti-position with those right lined up. Let's look at a Newman projection just to show one more example of what I mean. I'm saying that if we have our hydrogen here, and then we have our rear hydrogens like this, that bonding must be happening right here in the front, right? So then the anti-bonding in the back is on the opposite side of this, right? So this is bonding as well, right here. So the anti-bonding must be right here, but in the back, right? Let me draw the red over top of it, this bonding interaction, so we can get this idea. Now you see that those line up, and so that electron is able to form that interaction, that sort of quasi-resonance, and that's what gives us increased stability in the staggered position, even more so than that interference. Now, why does this matter? Well, it's really important because imagine, for example, that we change everything right here and say, hey, this is no longer a CH3 here. This is now a CH2 and it's a carbocation, right? So what would the structure then be? Well, that means it would have a hydrogen flat out here, and this would be trigonal planar with two hydrogens like this. And then we would actually have an p orbital that's empty. Now what it turns out is that these electrons, of course here, are able to hyperconjugate or line up and donate electron density to that p orbital and stabilize this carbocation a little bit. It's really important, and it's going to come into our future chapters, but I want to introduce that idea of hyperconjugation now so you understand what it is and what it's doing.